Swayam Prabha. Digital India. Educated India.
Good afternoon, everyone. We are doing module number 6, that is micro texture measurements using EBSD technique in SEM. So, this is lecture number 34, that is quantitative evolution of Kikuchi diffraction pattern, and this is part 3. So, the concept that I will try to cover in this lecture is, we will continue with understanding Hauff transformation techniques, and we will go ahead and try to understand a little bit about in real life scenario, that is in the SEM EBSD, how basically Hauff transformation is done using image correlation technique, and basically which I will say that it is a gray tone weighted transformation or radon transformation developed by Radon and co-workers. Later we will try to understand the Krieger-Larsen method of peak detection in Hauff space, and this will give you all an idea that how in EBSD the Hauff transformation basically is used to calculate the orientation and to extract information about the quantitative microscopy. So, let us go ahead. So, as I said in the last lecture that the band which is present in the Kikuchi pattern, the bands. So, one of the band is basically a bright line, the bright line in the pattern space. This bright line, which is the Kikuchi bands, are basically transformed into bright regions of the Hauff space, and this was shown by Kunje et al. In 1993. Now, these bright spots can be detected and used to calculate the original positions of the band. Now, you see that using that calculation that the band will have a particular rho and theta, a point in a Hauff space, that is the rho theta space is determined, and from the point a back calculation is done to determine the position of the band. Now, why it is done so? Because usually the band sometimes it could be sharp and it could be diffused, as I said, but once the bands are transformed into a point, it becomes very prominent, and back calculating the position of the band from these points make the bands also very prominent, right. So, it can be used to calculate the original positions of the band. So, as I said that it is obvious that location of point from a diffused band and back determining the band makes it more accurate, right. So, one can determine those Kikuchi bands or lines more accurately. Now, this reduces the challenge to find the band in the diffraction pattern to a peak of high intensity in the Hauff space, right. Now, so even the poor pattern quality, the Hauff transformation gives slightly more accurate results, right. So, if you look, we initially have to record the Kikuchi pattern, and after recording the Kikuchi pattern, there has to be a little bit of pre-processing. So, there are the first pre-processing has to be done, and you will see that when you will go to take a sample and do a EBSD measurement in a SEM in a scanning electron microscope, then you have to do a background subtraction or division, and the name may vary depending upon the the company's microstructure microscope it is and the EBSD it is. There will be systematic way to improve the contrast. Sometimes pattern energy is considered to improve the quality of the indexed pattern in a Kikuchi pattern image. Now, a Kikuchi pattern image, you see I have shown here a schematic of it, and say for example, it is an average of the thick Kikuchi band, and that is the average of the Kikuchi band, a line like this. And as I shown in the last lecture class, that a perpendicular to it from the origin, and how the origin is? Origin is basically the center of the initially a rectangular pattern is taken on the phosphor screen, and then it is converted into circular pattern. So, that circular area is only taken, and then the center of that circular area can be considered as the origin, and from that origin one can calculate rho theta with respect to each band, right. Now, the rho theta is the vector perpendicular from the origin to that band, then that has an angle theta with respect to the x axis, and if we put the sample in a correct manner, this x axis should be almost equal to the parallel to the rolling direction, right, for example, for a rolled sample. So, that we can know how to have the the rotation matrix between the crystal frame of reference to the pattern and the pattern frame of reference to the sample frame of reference, and that is how we find out the orientation. Now, let me take the pen initially, and let me try to show you that what I want to show here. So, if you look into this Kikuchi band, the position of this line, which is basically perpendicular to this band, is converted into a spot somewhere here, and this spot is such a way then that it has a rho and it has a theta, and this is the Hauss space. Now, this Hauss space is obtained in such a way that you see that, as I said, that a line in a Kikuchi pattern is transformed into a point in a Hauss space. However, you see if we draw a band like this, and let us say that let us take a point in the band. A point in a band of the Kikuchi pattern space is converted into a sinusoidal curve in the Hauss space. And how it is so? A point in a Kikuchi pattern consists of multiple numbers of lines. It can consist of multiple number of lines, an infinite number of lines, and each of these lines will have certain rho theta relationship. That means, if we take any line like this, it will have a certain rho theta for which that line will be perpendicular to, and therefore, each point, let me change the color, right. So, here it is blue. So, each point of this Kikuchi pattern may have an infinite number of lines passing through it, and each line will have a certain rho theta, right. and this rho theta corresponds to a sinusoidal curve in a half space. In a similar manner, if we look into another point, say this point, and if we say that okay, there is another point somewhere here, and this color green is just for you to understand, then in this position also there will be several lines which will cross this point, and each of these lines will have certain rho and theta, and therefore, it will construct another sinusoidal curve, and like that several points will be at several positions, and we have shown some red and violet colored points in the Kikuchi band of this Kikuchi pattern, and each one will produce a sinusoidal curve, and each one that will produce this sinusoidal curve will meet at a certain point, which is basically equivalent to the rho theta corresponds to this particular band, and this point basically is the point which is determined to be the rho theta point for that particular band. If you look into this pattern, it has a butterfly like shape, and therefore, it is called butterfly filtering of the Kikuchi band into a half point in a half space. So, the transformation of the pattern, like each xy point of the Kikuchi pattern image into a sinusoidal curve in the rho theta accumulation space is basically by which the half space is created. So, as I said that in this case rho is equal to x cos of theta y sin of theta, right, and it specifies a line which is at an angle theta from its normal, and the angle theta is with respect to the x axis, which is r d. So, you see that image correlation techniques are used in order to convert all these lines in terms of points, and they form, because of this kind of calculation, each point of the Kikuchi pattern lines are converted into sinusoidal type of curve. It looks like butterfly pattern, and this butterfly pattern will have a certain intensity, because you see the intensity of the Kikuchi bands are converted into this butterfly type of pattern, which is basically highly intensified at a small region, that is a point which is rho theta point of the half space. In this way, even if any Kikuchi band has a little lower contrast, the automatic pattern recognition easily recognizes the those patterns, because the intensity of the half spot is a little more prominent than the the intensity of the Kikuchi bands, and this helps us to directly determine the zone axes of this Kikuchi bands too. Now, you see that the method by which actually the Kikuchi bands are transformed into half space are basically known as gray weighted half transformation, or you see radon transformation. Now, the intensity I x y corresponding to the Kikuchi pattern, that means this pattern, right, at each pixel of this Kikuchi pattern, that is each pixel of the EBSD is added to the value of intensity in the rho theta space. Okay. And initially of this transformation, this rho theta space is set basically to a 0 intensity. Now, you see the actual Kikuchi band of a finite width produces a peak of a finite extent, right. So, you see a band which will have a certain width, say for example, a finite width will that high intensity band will transform into a intensity peak in the Hopf space to a to a finite extent, right, and this extent will be like a sinusoidal, a multiple sinusoidal curve which looks like a butterfly type pattern, and therefore, it is known as butterfly filter to obtain a bright spot. So, how transformation basically gives more prominency, more prominent band in EBHD. So, what do I mean is that a Kikuchi band which could be a diffuse band is taken, and then it is transformed, the intensity of maybe a very diffused intensity of that band is transformed into a spot using this butterfly filter to obtain a spot which is relatively more intensified, relatively more observable, okay, or distinguishable, and therefore, back calculated to obtain the actual position of the Kikuchi bands. So, the calculated Kikuchi bands are more prominent, right. So, for obtaining homogeneous transformation, very important thing, as I said in the previous slides also, first a circle with a certain diameter, is taken from the rectangular pattern that is obtained, means rectangular Kikuchi pattern that is obtained for this Hopf transformation technique, right. Identification of peak of the Hopf means identification of the bands in the Kikuchi pattern. The bright line in the Kikuchi pattern, if it is considered to be 1 pixel thickness or width, becomes a single bright point in the Hopf transformation, right. So, in case of electron backscatter diffraction in an SEM, while the sample is tilted at 70 degrees, the phosphor screen is basically kept at 90 degrees and it is away from the incident beam. Now, in this case, you see identification of the Hopf space rho theta points are done from the obtained Kikuchi bands, and from this Hopf space the constructed Kikuchi bands are obtained. So, the corresponding constructed Kikuchi bands are obtained, and this constructed Kikuchi bands width, right, which basically is equal to 2 theta, is determined for that specific working distance, means the working distance of the sample with respect to the electron gun, the exact tilt of the sample, which is most of the time 70 degrees, the distance between the sample and the phosphor screen, right, that is the the camera or the detector. So, it is basically what we have, we already in the software there will be computed list of bands, okay, all the bands for the same working distance, for the same tilt angles, for the same distance of the specimen with the phosphor screen. So, now these computed list of bands are compared with the constructed Kikuchi pattern that is obtained, and then all all possible bands are compared, that, and then the different HKL planes corresponding to these Kikuchi bands are calculated. So, see, EBHD software database will have to contain all interplanar angles for a certain material. So, it will have the database of each and every material for which the crystal structure is known, right. and it will be specified priori, and even if it is not specified for certain alloy or certain compound ceramic or something, one can make it using the information about the crystal structure, its Wyckoff number and other things. One can make it in that in the you see the software. So, there in new softwares there are places where one can just make this information, and then the software can compute the list of bands that can form for different working distances, different tilt angles, distance between the specimen and the phosphor screen. So, after we obtain the half space and we construct the Kikuchi band, that means, once we have indexed the Kikuchi bands, the zone mixes can be determined between two bands, and thereby the ND can be determined, and thereby the RD can be determined using the formulation that we show in the last to last lecture, and thereby you see the software also calculates the orientation in the using the EBSD. So, finally, Kriegel-Leschen in 1998 he did a more refinement in the peak detection technique in the Hauff transformation. Means he wanted to determine the location and the particular width of the Kikuchi band. So, Hauff transformation, the Kikuchi band contains two lines, right, and it has a thickness. So, Hauff transformation is done for both the lines. So, the detected bands are listed according to their relative intensities also. So, the Hauff transformation is done for both the lines of the Kikuchi pattern of a Kikuchi band, and then for each band, each detected band, the intensity is recorded, or each band is listed according to their relative intensity, and the bands with highest intensities are used for further orientation calculations, etc. right. So, the bands with higher intensities are used to do the orientation computation. Now, you see that sometimes what happens, if as you have seen that only 3 bands are required to obtain the orientation information, but sometimes what happens that recording only 3 bands with higher intensity, and sometimes indexing of this band becomes wrong, okay, or wrong bands are detected. So, you see mainly when it can happen when the electron beam is falling on a surface which may have a dislocation bending, lattice bending due to dislocation presence, or in the grain boundary. So, nowhere near to the grain boundary sometimes. So, nowhere ambiguous solutions may be obtained. Now, therefore, in order to get more refined information, sometimes additional consideration of bands of lower intensities has to be considered, okay, so as to eliminate wrong solutions. So, there could be possibility that more than one solutions of a zone axis could obtain from the Kikuchi bands or Kikuchi pattern. So, in order to identify the zone axis unambiguously, all possible combinations of this at least 3 different bands that is needed are obtained, okay, and the solution is formed based on the closest match in terms of the interplanar angles as obtained from the tolerance between the computed and the measured interplanar angles. Okay. So, you see that the intensity, what we can conclude from this lecture is that the intensity of each pixel of the Kikuchi pattern is transferred into bright regions of the Hauff space, and from which the Kikuchi bands are basically back calculated for more accuracy. These Hauff spots are bright regions which forms by intersections of the sinusoidal curve formed from each points of the bands of the Kikuchi pattern, right, and they have the butterfly shape, therefore, they are sometimes called butterfly filters. Hauff transformation can be generated for both the Kikuchi lines of a certain Kikuchi bands to determine the location and particular width of the Kikuchi bands given by Krieger relation. Then all possible combination of the three different bands are obtained and the solution is formed on the basis of the closest match in terms of the interplanar angle as obtained from the tolerance between the computed and the measured interplanar angles. Okay. Thank you very much for this class.